Hi, Irrelevance. So we've talked about rates of change and how calculus is related to that. Constant rate of change here, and then we talked about average rate of change and instantaneous rate of change. So let's think about the idea of a limit. If we consider this curve here, and we've got 2 points on this curve, we've got A and we've got B, and we consider the slope of the chord AB, and then we also consider the slope of the tangent at A. Now remember, the idea of a tangent is something that just touches the curve at one point. So in this example, our tangent would look something like that. It touches, it doesn't cut, and it just touches at A there. You can see that as B approaches A, so as this point B, if we moved it and it became closer and closer and closer to A, like that, the slope of the chord joining A and B, so the chord is just a line that joins 2 points on the curve, so the slope of that curve as B gets closer to A is going to approach the actual slope of the tangent. You think about it, if we move B down to here, then it would look like that, and that would be closer to the tangent. If we move it even closer, that slope of that chord becomes closer and closer to the actual slope of the tangent. So we can say that as B approaches A, the slope of the chord approaches the slope of the tangent. So when we're running that in terms of a limit, we can then say that the slope of the tangent is in a way limited by the slope of the chord. That chord, the slope of it is an approximation for the slope of the tangent, and as the point on the curve gets closer and closer to the other point, that chord slope is going to get closer and closer to the slope of the tangent. So we write that as the slope of the tangent is the limit as B approaches A of the slope of the chord. Because that means provided that. One more example of that. So let's thinking about calculation of limits. And remember, when you're calculating a limit, it's like you're calculating a slope. If we've got the example here, the limit as x approaches 5 of 3x plus 2. That's how we read this. We say the limit as x approaches 5, that's the x arrow to 5, of 3x plus 2. When x equals 4.5, so that's somewhere a little bit further on from 5, before we get to 5, 3x plus 2 is going to be 3 times 4.5 plus 2, which is going to equal 15.5. Now if x equals 4.9, we work that out in exactly the same way and would get 16.7. And when x equals 4.99, so even closer to 5, you get something like 16.97. Now, notice that if we substitute x equals 5 into 3x plus 2, we get 3 times 5 plus 2, which is 17. So if we substitute in the actual number, so this brings us to what we call the first rule of limits. The first rule of limits states that if on substitution a real number is achieved, then that value is actually the limit. This actually only occurs though because 3x plus 2 is what we call a continuous function. So it won't always occur in this way. Not all limits actually can be found using substitution. So we've got some examples down here of limits that can't be found using substitution, and which we have to do a bit of an extra step in order to be able to do that. So if we think about the limit as x approaches 1, and it's a bit hard to see, but the limit as x approaches 5 of 2x squared take 10x over x take 5. So if we think about when x equals 5, let's substitute that in, we get 2x squared take 10x over x take 5, and let's substitute in when x equals 5. We're going to have a problem which you can probably spot already. The problem is that we're going to get a 0 on the bottom. So we're also going to get a 0 on the top. The answer to that is actually 0 over 0. That's meaningless. Alright, so that doesn't work because that is not a continuous function. It doesn't exist for all values of x that we're considering. So we have to do something extra to that to be able to actually work out the limit as x approaches 5 of 2x squared take 10x over x take 5. Remember, when we're talking about the limit, we're really talking about the slope of the tangent, alright? So we want a way of approximating the slope of the tangent to a graph at a specific point. In this case, it's the point x equals 5. What we can do, so if you get something like that, factorize. We've got the factor of x take 5 on the bottom there. Let's see if we can get a factor of that on the top. We're going to factorize by taking out the common factor of 2x, and we get 2x bracket x take 5 over x take 5, the limit of that. So that's provided that x is not equal to 5. What we can just do is we can cancel that. And that limit then is going to be 2 times 5, which equals 10. Alright? So what that means is, as x gets closer and closer to 5, 2x gets logically closer and closer to 10. So if we think about an actual graph of this function up here, what it would actually look like is this over here. It would look like the function 2x, but at the point 0, at the point 5, it doesn't exist. So it's identical to 2x, other than that point 5, which is the point 510. At that point, it doesn't actually exist. That's a missing point. It's called a discontinuity. And so that's why you can't just use substitution in that case, because it's not a continuous function. Alright, so this gives us a bit of a general rule that we can think about for functions. We've already got one up here, that if on substitution a real number is achieved, then that value is the limit. So if you get a nice number, that's your limit. Another rule now that we can think about, that is if a, so a is just a number, if a causes the expression to be indeterminate, x take a will be a factor of both the numerator and the denominator. So that's a really useful rule. Let's do some examples that show where we can use that. If we've got the limit as x approaches 3 of x squared take x take 6 over x squared take 9. Let's try and substitute in 3. And immediately you should see the denominator will become 3 squared take 9, which is 0. So you'll get something over 0, that's indeterminate, that's undefined, you can't do that. That therefore means that x take 3 must be a factor of both the numerator and the denominator, because a is causing the expression to become indeterminate. So therefore all we have to do then is factorize, and we've already been given one of the factors. That limit is actually going to be the limit as x approaches 3 of, we know it's got to be x take 3 on the bottom and x take 3 on the top. Now, if you recognize the bottom is x squared take 9, that's a perfect difference between two squares. So it's going to factorize to be x take 3 times x plus 3. And on the top line, all we've got to think about is, what do I need to multiply by to be able to get those values? Well, obviously negative 6 has to come from this number, negative 3 times by something. So that's going to be times by positive 2. So this must be x plus 2. And if you check that, you'll see it works. That means that this function actually exists, provided that x is not equal to 3. Alright? That function exists only provided that x is not equal to 3. Make sure you write that in, x not equal to 3. So that means I can cancel them. Obviously I can't do that if x is equal to 3, because I'd be dividing by 0. And so then I can substitute. I can just do substitution again. So I factorize it, I get rid of the interfering expression, if you like, and then I substitute, and I'd get 3 plus 2, which is 5, over 3 plus 3, which is 6. And so that's my limit. Let's do another one. This one's the limit as h approaches 0 of h cubed outside of 2h take 1. Now if you look at that, you're going, I don't see any problem with that. You're right, there's no problem with that. You can just use the first rule of limits, which is substitution. If you substitute h into that, you will just get 0. So the answer to that is simply 0. 0 is not the same as 0 over 0, so don't get those two confused. A bit of a harder one down here. This time we've got the limit as h approaches 0, but you've got h on the bottom. So we do the same thing. We're going to factorize by removing a common factor, and then we're going to substitute. So factorize, remove a common factor, and then substitute. And what we will get if we do that is we'll get a top line which says the limit as h approaches 0 of h outside of 2 take 3h plus 4x all over h. We've just taken our h, we're going to cancel the h's, get it off the bottom line, and then substitute h equals 0. And when you get that, do that, you'll get 2 plus 4x. Again, this is provided that h is not equal to 0, otherwise you can't be cancelling. So put the last example, and this one's designed to be a bit of a trick. We've got limit as x approaches 2 of that expression. We're going to substitute in 2 to the denominator, work that in your head, and you'll get 0. So again, no good. Let's try factorizing. 2 makes it an issue, so that means that x take 2 must be a factor of the bottom and must be a factor of the top. The top's easy. We've got to go x take 2. What's a number we can multiply negative 2 by in order to get positive 10? That's negative 5. So we're going to get x take 2 times x take 5 up the top. On the bottom, what's a number we can multiply negative 2 by to get 4? Well, that's negative 2. Alright, so we can do this provided that x is not equal to 2. We're going to cancel x take 2 and x take 2. But then, as x approaches 2, x take 5 on x take 2 approaches negative 3 over 0, which is undefined. What does that actually mean? Well, that means there is no limit. We cannot calculate an approximation for the slope at that point. Alright, there is no limit, and that's perfectly legitimate. There's no limit to that function at that point. Okay, so that's the idea of limits. Enjoy.